Welcome back to physics. This is session 5 together, electrostatics. Now, this is quite a critical part of the syllabus. You know, the magnetosphere and that's great. We're not going to feature much on that at this point, but we've got to remember that the charges cause spinning electric charge causes a magnetic field. A moving magnetic field can cause an electric charge, electric field. Have you ever wondered, we're going to talk about a topic now. This is the key, this is a core part of electrostatics. This is a core part of the syllabus and something that is going to go into next year as well. Now, have you ever wondered why, if you blow up a balloon, rub it, it starts picking up pieces of paper and pieces of plastic and things like that? That is essentially electrostatics, okay? Let us go and let's look at an atom. In an atom, remember we've got a couple of protons, maybe a couple of neutrons as well. And by now you should be able to tell me what element that is. 4 plus. So how many electrons is it going to have? It's going to have 1 s2 and 2 s2, okay? So it's going to be 1 s1, 1 s2, right? And 2 s1, 2 s2, okay? So it's going to be number 4 electrons. So it's going to be hydrogen, helium, lithium, beryllium. Doesn't really matter what it is, okay? But I'm just bringing the physics and the chemistry part together. So what are we saying? We're saying, right, there's that. Now, when we take our balloon, okay? When we take our balloon, now I'm actually going to use one of these here. Okay. When we take it, let's pretend this is a balloon. Or let's just say it's an atom with the electrons over here. Now we come along, these electrons are all sitting on this, right? And we rub it. Well, what do? These electrons here are very small, very light. We actually rub them off. No, we don't rub them out. Okay? We can't, because you can't create nor destroy the electrons or whatever, okay? Now, what happens when we rub it off? Where does it go? What does it leave behind? Well, if I rub off 2 electrons here, I'm left with this, aren't we? Neutron there and there, okay? And we're left with 1 s2. So we're left with an electron here and an electron there, right? What is the charge on this is going to be? The charge is going to be plus 2. Why? Well, plus 4 in the nucleus, plus 2 electrons means I'm left with a charge of plus 2. So my ruler has become positively charged. I have wiped the electrons off it. Okay? Now I go to another ruler and I take my cloth and wipe it over that ruler. And what do? Well, I do this. All right? Let's just keep the same stuff. All right? There we go. 1 s2, 2 s2. New ruler. Now I come along and I wipe an extra 2 electrons. So I add 2 electrons. So now I've got 2p2. Right? What next? Well, now I've got a charge in the nucleus of plus 4, but I've got minus 6 on the outside. So I've got a negative 2 electrons there. Here I've got plus 2 protons. Here 2 electrons extra. So here my new ruler has become negative and this one has become positive. Okay? You notice anything yet about physics and chemistry? The electron is schizophrenic. Okay? That's really the sum total of it. It's tracking the electron and finding out where he goes. Okay? In physics, we move them. In chemistry, they must all add up and balance out. Okay? So here, now I've got a positive and I've got a negatively charged something. So what can I say? I can say this, can't I? I can say, right, here I've got, my ruler has got a plus 2. This ruler has got a minus 2 charge. Why? It's got 2 electrons on it. Where did they come from? I pinched them from there, right? Now, if I bring these two together, right, I bring them closer and closer together, all right? What happens here? This is plus 2, minus 2. These want the electron back. They say, come here. The electrons go and sit here. They want to go back. All right? Because the natural order of things is that it would be uncharged. Okay? Doesn't want to be charged. It wants to be uncharged. It's happiest uncharged. Why? Because it's an element. Okay? It's in its element when it's an element. Which means it wants its electrons back. So what does it do? It pulls and says, come here. So I get a force. We get a force between these two. All right? We get a pull. Because we're saying, come back, electrons, right? Come back. Pulling them back. So we've got here the same as magnets, north. Similar, it's not exactly, but similar. We've got a force. So we've got here an electric field. Right? Because this is pulling that. It's the same principle as a magnetic field. All right? Well, how does this happen in nature? Well, many of you must have brushed your hair in the winter, or taken a jersey off or put one on in the winter. And if your room's dark, you see sparks. Okay? That's these static electricity electrons moving around. Lightning itself is in fact static electricity, and it's a discharge. It's the electrons joining the protons and creating a stream of electrons flowing one way to meet each other and re-establish a zero charge. Right. So, what have we said? We've said, okay, essentially over here, okay, static electricity is the hairbrush, okay, clothes on carpets, dry air in winter causes static electricity. You walk across a carpet and then you reach out and touch the door handle and you hop around in pain because you just got burnt by static electricity, which is what happens, okay? It's quite a potent little charge, all right? Let's have a look now, all right? We said how they get charged, okay? Now, in the interim, for example, if I have left behind, let's say 5 positives here, my cloth has got 5 electrons on it, right? And then I go and I rub onto this one, I rub 2 electrons. My cloth has still got 3 electrons on it, hasn't it? Then I can go and rub something else, I can rub those 3 electrons off. Okay? So I don't have to have equal charges on things. We can make something charged up. But the basic charge, the basic unit of charge in all of this, okay, is 1 electron. Okay? And the charge on 1 electron is minus 1.6 times 10 to the minus 19 coulombs, because the charge is measured in coulombs. So the unit of charge is called the coulomb. Okay? That is the unit of charge is called the coulomb. Right? Now, apart from, let's say, rubbing charges on and off, you can also get radiation. Okay? I'm just mentioning it because some people want to know about it. Radiation, you get alpha, beta, and gamma. Okay? The alpha is a helium nucleus. The beta is a stream of electrons. Electron stream, okay? And this one is a photon. Okay? Photon, remember those? This is a light. Let's say flash. Okay? Of course, the photon, the light, could be X-ray. It could be in terms of, let's say, high order UV. It can be that kind of photon coming in. Right. So now, well, what are we going to do with this, okay? All right. We've said that in electrostatics, okay, if we've got a an item which is, let's say, positively charged over here. And we've got, this has got plus 5, okay? Which means it's 5 electrons missing, okay? Now, over here, all right, we've got another element here, which has got, let's say, minus 3, which means I've got 1, 2, 3 electrons. Let's put our charge over there, shall we? We've got 3 electrons over there, okay? Those 3 electrons over here is a minus 3 charge. Can you see the charge here is 3 of the electrons, which is 3 times 1.6 times 10 to the minus 19 coulombs. So the charge Q is number of electrons times 1.6 times 10 to the minus 19. A minus, right? So the total charge is the number of electrons times the charge on one electron. Similarly, the charge here is going to be 5 times the charge on a proton is exactly the same, but plus 1.6 times 10 to the minus 9. Why is it the same? Because elements are uncharged, and the charge on a proton equals the charge on an electron. It's an uncharged element, right? Can you see how the physics and the chemistry are aligning with each other now? Which is how it should be, okay? The one is explaining the other. So the charge is the number of protons times the charge on one proton. Okay, that's what we've got here. So what are we going to do? We can now charge things up. Well, we can charge them up using a stream of electrons as well. Essentially, that's how cathode ray tubes, the old TVs, worked. It was a stream of electrons that were bent through magnetic and electrical fields to spray across the front of a surface that was coated, and it gave off photons, essentially. All right. So we've got here this number of protons times and number of electrons times the charge on one electron. So we measure everything in coulombs, all right? Now, we've got here, what we said is we've got a plus, let's say, and a minus. We said they attract each other like this. We always draw our arrow from positive to negative side. All right? Like that. This means it's trying to harpoon it, so this is a traction, isn't it? It's pulling it back. What is this one then? Plus and plus. This one we always draw from the plus, but this one pushes it away. So this is repulsion over there. They push away. Okay? Push away. Obviously, right? Then, if you look at it, okay, a negative and a negative. How do we deal with that? Oh, hang on. We always draw from the positive to the negative. So we've got this. Because we know negative must repel each other. All right? That's what happens, okay? Now, we know that this repulsion is the same as a magnet. We get a force. Right? Why? Because if you charge up this balloon or a ruler and you put it near a piece of a hair or paper, it lifts it up. All right? How do you lift something up? How do I lift this up? I have to use a force to pull it up, don't I? Don't worry, we'll get to this guy soon when we do mechanics. But we're lifting it up. So there is a force. There's a force that is actually very real. It is able to pull it up. This force, okay, we say, what is it dependent upon? Well, let's think of a magnet. Very strong north pole, very strong south pole. Big force. So the force must be proportional to the charges, right? Because you are actually going between a charge Q1 and Q2. Remember, you've got, this one's got a charge on it, a plus and a plus and a plus. This has got minuses on it. There's a force of attraction between these, isn't there? So this one's trying to pull these electrons back. It's trying to pull this whole thing close enough so they can jump across and come back to their rightful place. This force here is proportional to, I mean, what if I had loads and loads and loads of positives and negatives on here? The force is proportional to the charges Q1 and Q2. Because this is the charge Q1, and this is the charge Q2, measured in coulombs, isn't it? So the force is proportional to the charge. But now hang on, let's go back to magnets, just as an analogy. If I put this here and this here, the force is very weak. So the force must be proportional to 1 over the distance. Okay? This is to the distance squared. It's called the inverse proportionality. Okay? Inverse proportionality, it's proportional to 1 over the distance apart they are squared. Okay? That brings us to what's known as Coulombs Law. Where the force is proportional to the product of the charges Q1 and Q2 divided by r squared, which is the distance apart the charges are. All right? And that brings us, finally, it's equal to F is equal to K, because in maths, how do we get rid of that? Remember in lecture 1 we spoke about it? We put it equal to and put in a K, constant of proportionality, Q1, Q2 over r squared. Okay? That is called Coulombs law, and that tells us how much the force is between the two charged particles, doesn't it? Okay? Now, let's look at a term called polarization. Okay? And then we're going to touch things together, touch them together, charge, quantify charge. Okay, we've already spoken about that. Okay, let's say I've got a rod, all right, over here, which is very negatively charged. I've put on here 3, 4, 5. I've put on here 3, 4, 5, 6, 7. I've got a charge of -8 there. Okay? -8, let's say coulombs. Doesn't matter. Okay? For this point. And I come next to this piece of paper or whatever. This piece of paper has got composed of atoms, isn't it? And each atom has got a plus and an electrons, correct? Doesn't matter what it is. It's got atoms. It's got nucleus. It's got protons and electrons. What happens as this comes closer? Right? As it gets closer, this had no charge on it, did it? As it gets closer, what does it do to the electrons that are sitting there? The electrons don't want to be here. So the electrons all go and sit on this side. Means that becomes negative, leaving the poor old protons over here. All right? This is polarization. We have, let me first use this word. We have created a positive and negative pole or side. Okay? We made it because this negative pushes the electrons away. Pushes away. That negative is pushing the electrons away, leaving protons, which means that now there's a force of attraction, right? That is the term polarization, okay? It's brought close, it creates it. That is how the things stick, okay? A polystyrene ball, for example. Let's just have a look at the surface of the balloon, shall we? We've got the surface of a balloon, all right? There it is. And this is a little uncharged polystyrene ball. The surface of the balloon, let's say, is now positive, right? Just for argument's sake, doesn't matter. What happens here? All the electrons now rush to this side, don't they? Because there's a positive, leaving us with a positive on that side. So that becomes positive, that becomes negative, which means that this is attracted. So the ball goes and sits over here with the negatives there and the positives over there. It attracts it and it sits onto it. There is a force of attraction there. And next year, we actually work with that force and we can see how much we can lift with a balloon of a certain charge. All right? Now, let's look at the last part of this, which is, let's say we've got a charged sphere over here. And for example, let's put in, okay, 1, 2, 3, 4, 5. We've got a charge of minus 10 on this one. Okay, it's negative. On this one over here, I have got a charge of, let's say, plus 6. All right? Right, so this is plus 6. Now let's have a look. Let's draw the electric field between them. All right? Well, we always draw from plus to minus. These are unlike, so they are going to attract each other. So we have a force of attraction because this gentleman over here is positive and that one is negative, but they are attracted to each other because we have a charge of minus 10 and plus 6. Now let us say we put them together. We just let them touch over there. All right? Remember, now we had that. What happens? Well, what happens here is, why have these attracted each other? Because this proton wants this electron back. So what happens on sphere A and sphere B? Well, sphere A had 6 positives, right? This guy here had 10 negatives. 6 of those negatives, 6 electrons come back to where they came from. And what happens when this occurs? The plus and the minus come together, and essentially we get a situation like this, don't we? We get a charge on B of 6 have gone, so we're left with 4 electrons, and on, let me rather put the 4 there, okay? And on this one, this is A, this is B, we are left with 0 charge, right? 0 charge, and this one's got minus 4. Everyone should be happy with that. It was minus 10. 6 electrons went to neutralize the charge on A, right? So we got minus 6 plus 6 equals 0. Now we are left with minus 4 on this one, aren't we? These are electrons. Where do you think these electrons are going to go? What they do is they do this. Okay, they are still touching. Here's A and here's B. 2 go sit there, 2 sit there. Why? Because they're electrons. They don't want to be with each other. They don't want to all sit there. They go and sit as far apart as possible. Right? So the electrons go and sit on the other side. Then we remove the 2. Okay? And we've got A and we've got B over here like that. What is the charge on B is now minus 2. And the charge on here is minus 2, minus 2. They are now, if we now, whoa, hang on, we're going to do the charge. We're going to do the field. This one over here is going to be it's negative, so positive. Can you see this? So we get repulsion. Force. So yes, you add them together, but it's very often easier to just think about it in terms of what's actually happening, right? Essentially, you're going to add them together, all right? That is essentially the Q final is equal to Q1 plus Q2 divided by 2. Okay, that's great. But you know what? It's actually easier to go and just follow the process down with the charges that occur. All right. What we've got here is the Q final there. The next piece is, remember, we said here I was going to look at the charge. We've already done that. We've already said, how do we work out what a charge is? A charge is measured in coulombs, right? And it's Q, and it's equal to the number of electrons or protons times either minus 1.6 times 10 to the minus 19 coulombs, or plus 1.6 times 10 to the minus 19 coulombs, right? It's the number times the charge on each. That is your charge. That's how we do it, right? Just as, remember, you got the law of conservation of mass, you equally get the law of conservation of charge. Okay, a charge cannot be created nor destroyed. Okay, it can merely be changed from one form to another, which means you're conserving charges. Okay, that's what this is premised upon. All of it is premised upon the conservation of charge. After all, what happened? You say, but hold on, I didn't conserve charge up here, because what I did, I added them together and then I neutralized. Yep, that is conservation, isn't it? Because what did we have? Let's argue the point, shall we? We had 10 minus 6 plus. Those 6 plus take and they change from a plus, go down to a 0 charge. All I've done is I've changed the state. I haven't created nor destroyed. I've just taken the minus and neutralized or added it to the positives. That's all we've done with it. All right? So that's the end of this section, all right, which is on electrostatics. Okay. The next section that we're going to be dealing with is electric circuits. Okay. Now, electric circuits, I'm going to show you a whole bunch of rules. We're going to talk about components. Then we're going to do a whole lot of examples on circuits, all right? Pretty much the beginning of where we're starting to do loads and loads of calculation. I think I've got like 20 different circuit problems over here to do. The last part is mechanics, okay? Where we're going to be talking about forces, forces moving stuff, forces accelerating stuff, and things like that, okay? I'll see you in session 6, where we'll finish off the electrical section, which is going to be electric circuits. Looking forward to it.